Well, I'm going to be talking about taking the next step after the tone mapping technique that Eric just presented, and that's how we can bring out the detail. And we're going to be covering deconvolution, stretching the image, using HDR multi-scale transform, linear histogram equalization, and sharpening. We've got a lot to cover. I'm going to talk rather quickly, so everybody take a breath because we won't get another chance. Okay, let's move that out of the way. So I have here an image of the Running Chicken Nebula tone map that I've already processed using techniques that are exactly what you just saw Eric do. I have a starless version of HA here that we're going to use a little bit later. We'll come back to that. And this is the original HA stack for that image. This is straight out of image integration. Nothing has been done to the image at all. This is exactly the way that it came out of image integration. And that's very important because the first step that we're going to do is deconvolution. I hear my buddy Eric groaning right now and saying, I don't do deconvolution. The reality is if you have really, really terrific optics and really, really crisp seeing, deconvolution may have limited impact on your image. But basically what deconvolution attempts to do, or really undo, is the convolution, is the obfuscation of the image that occurs whenever we record it on a sensor. We've got the skies, we've got our optics, the sensor, all of these things tend to convolve the data, and deconvolution uses what's called a point spread function to deconvolve, to undo that damage that was done to the image. And so that's the first thing that we're going to talk about, is how we produce that point spread function. A point spread function is a response to a point input. So if you're talking in general about what a point spread function is, we give it a pulse, see what happens. Well, the great pulse that we have in our images are stars. They are exactly a point of light source. And if we look at what happens to the stars, we can see how the atmosphere and our equipment is convolving the image. Now, it used to be that the way that you produce this point spread function was to go into this function right here called dynamic PSF, and you would go and select star, 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 and find a bunch of stars that would fit a particular set of parameters and would give us a good point spread function. That was a very time-consuming process. And quite frankly, it was messed up more often than not by most people. And thanks to the efforts of a wonderful human being who I've never met named Hartmut Bornemann, he pretty much condensed all this down into a script that will create our PSF image for us. And what this script does is it applies those criteria that we're supposed to apply in order to get good stars. You say how many stars you want to use, and 50 is a perfectly fine number. And you click on this evaluate button right here. It'll go out there and look at all of the stars in the image and come up with the right stars to really quantify and identify this point spread function. And then when we're done, we can view the stars that it chose, and we can click create, and it'll create the PSF. Now that takes a few minutes to run, and we're short on time. So I've already done that. And what we get is a point spread function that looks like this. This is how the PSF it has been characterized by producing that image, that PSF image. That's going to be important for running deconvolution in a minute, but it's only one step that we need. The other thing that we need to do is we need to worry about something called de-ringing. If I pull up deconvolution here and just turn all of this off, maybe I'll just explain this by way of demonstration. But if we go ahead and apply deconvolution right now, without having any de-ringing at all, we get these little artifacts, these little ringing artifacts around the stars, and basically what you have there is a mathematical principle, and I forget the name of whoever the guy was that figured out what that was. I don't remember, but anyway, there's mathematics involved that tells us why we get this ringing, and there are ways to undo the ringing. One of the first things that we do is we use this global dark and global bright to set up a global de-ringing model. These are typically very small numbers. When you first start the deconvolution process, the number's way too big. I think it's like 0.1. way too big. So you usually end up turning this down and fooling around with these numbers back and forth until you get a global de-ringing model that removes the ringing around these stars. And the other thing that we do is we use this local de-ringing. What that does is it uses what's called a local support file to kind of focus in our efforts on de-ringing. That local support file, in effect, is a star mask. And so I'm going to show you how we can produce a really great star mask really quickly with this linear, unstretched data. So what I'm going to do first is create a copy of the file, and I'm going to use multi-scale linear transform. And what we're going to do is change this to 5 layers, and we're going to turn off layers 1 and the residual layer. And when we run that on our image, what ends up happening is we knock out all of the nebula. We knock out all of the noise. You'll see if I zoom this way up, we don't have any noise left in there. And all we're left with are the stars, right? Because we've pulled out those 2 layers, where not layer 1 where we have noise and the residual layer where we have everything else. Now we've helped the star mask creation process to work much more efficiently, and we'll end up with a better mask. So I set a noise threshold here of around 0.1. The scale that I want for this is a scale of 3. I don't want a lot of large scale growth for this de-ringing map, so I set that around 1. But small scale growth, we do want to protect the smaller stars, and they're not really that bright, so we do want some small scale growth there. Compensation value of 2. We want it to be pretty smooth, and we want to make sure that we turn on aggregate and binarize. These 2 options will help brighten up the star mask. So if we go ahead and execute this now, you're going to see what I think is a pretty good looking star mask pop out of this. There we go. And this is going to be our local support file for our de-ringing function. We're going to get rid of this image that we used to create it. We don't need that any longer. I'm going to call this, what did I call it? Wait, let me just check, so I don't have to do this twice. De-ringing support. So we're going to call this de-ringing support. Oops. If I could type, I could call it that. There we go. And we're just going to put this aside for a moment. We'll move that over here. So now it's time to run deconvolution. Now, something else that you'll see if you go and look for tutorials online is that a lot of people use masks for deconvolution, where they mask off the brighter areas. I submit to you all that that is not the way that the developers at PixInsight have envisioned this tool, and we should not be using masks to do deconvolution. And I'm going to show you how to do deconvolution where we don't introduce any noise and where we have nice pretty stars. So right now we've got our de-ringing set up with a global dark, a global bright, and we have our de-ringing support file. You can adjust this amount slider and play around in a preview until when you apply your deconvolution, as I've just done, we still have nice pretty stars. See, we don't have any bouncing. Here's before and after, before, after. We don't have any bouncing going on in the stars. The stars are tightening up nicely, and I don't know if it's coming through on the YouTube show. I know that it's kind of hard to see sometimes, but if you look at these areas of nebulosity, we go from this soft kind of appearance to something that's a little more sharp, right? A little sharper. We are introducing some noise though, and you can kind of see it there, and you can really see it in low signal areas where there's some noise in here. And this is the reason that most people incorrectly use a tool, run to a tool that they're familiar with, which is a mask, and they mask off the low signal areas. The better option is to use regularization. Now, wavelet regularization and the regularized Richardson-Lucy algorithm is how you should be doing this. Now, I usually start with around 3 layers, and I set them at 5, 3, and 1. For the noise reduction. I always use a Gaussian model, not a Poisson. So if we go and execute this now, you'll see that we've gotten rid of, as soon as it finishes running, we've gotten rid of all of that noisy stuff that was floating around in there before. We have nice smooth gradients, nice smooth transitions. We still have the definition before and after that we were after here, and our stars look great. So here we are ready to run now on our whole image. Again, this is going to take a few seconds. I didn't want to wait and spend the time. So here is our fully deconvolved image. And if I zoom in on this, oops, on some of this here, let's zoom this up a bit. We can see, if I do a before and after there, you can see the result of our deconvolution. If I move to an area that is, let's go over here, that is, more low signal, you see that we haven't introduced any noise, we haven't increased the noise in the image, and we use no masks. That, in my opinion, folks, is the right way to use deconvolution. I'm just going to rename this little bugger L, and we're off to the races. Now you might say, well, that was a pretty small change. What we're after here is small changes, because we're going to do a lot of things, as I said in my introduction there, that are all going to incrementally improve the sharpness of this image. So we want to take little bites at the apple. We're not looking for a big dramatic holy cow moment. We're looking for small incremental changes as we go through the process. So that was our first change. Now let's stretch the image. I'm going to turn off my screen stretch here. There we go. And I will bring up my stretch. Let me make this a little bit bigger so that we can see what we've done. There's my histogram. And we'll just bring it up in a preview here. And you can see what I've tried to do in my screen stretch is bring the black point right into the bottom of the blacks, right into this hip right here. And we slide our white point down until we get to the point that we're filling up the image. We don't want to go too bright. We don't want the thing looking like this, right? And we don't want to go too dark, because we won't really see the beauty revealed in this nebula. So we just want to get it to be something like that, somewhere around there. Should be a good look at our image. And I'm going to go ahead and apply that. Now we are no longer working with a linear image. This is a non-linear image at this point. Okay. So we're starting to see, if we blow this up a little bit here, we're starting to see our detail come through. We're starting to see the beauty that we're going to be able to reveal. But we've got these areas that are kind of bright, like right here and right here. And if you look closely, and I don't know if it's coming through on the YouTube video, but there's detail in there that's really being sort of obfuscated by the fact that the nebula is so bright. And we could really benefit with some what's called dynamic range compression. And for that, we're going to use the HDR multi-scale transform tool. That's what this tool does, is compress our dynamic range. And if I yank up a preview here, we'll take a look at this. Again, what this tool does is compress our dynamic range. I think by default, when you go in, it's set for 6 layers and a scaling function of B3 spline, and lightness mask is turned off. Excuse me. We definitely want to turn on our lightness mask. We want to apply this to the brighter areas of the image. That's the whole point. And I just sort of play around with the number of layers in the scaling function until I get what I like. And so I might go ahead and run this and take a look and say, well, okay, that looks all right. But let me see what happens if I knock the layers down. Ooh, no, that got a little too flat. I don't like that very much. Let me just knock it down a little bit and see. Yeah, that's starting to look a little bit better, but I think let's see what does small scale look like? Let's take a look at that. And I just kind of fool around like this until I get to the point where I'm getting the kind of results in the image that I want to see. And if we go back to the full image and I get rid of this preview here, make it a little easier to see. When we apply this, what we're going to see is we're going to knock down all those really bright areas in the image, and we've pulled up just a ton of additional detail in all this nebulosity here. You see all these little bands of detail that, we could kind of make out before, but they were sort of like little wisps, and we couldn't really tell what was going on, right? So now we've pulled those out. But what have we done? Well, the downside of this is the image looks kind of flat, doesn't it? We've kind of lost our depth. We've kind of brought this whole thing down to sort of the same level, and we're missing that depth in the image that kind of gives us that that kind of feeling like we're looking into the screen. So it's time to bring some of that back. And for that, I'm going to use the LHE, the local histogram equalization process.
A quick question first, or
sure.
maybe maybe we're not quick.
Yep. Yep.
A question from Linda. She says, my understanding was the de-ringing support was primarily to protect just the largest stars from ringing that the global setting couldn't handle. So it should only include the biggest stars. What's your take on that?
That is what I've heard Adam Block say in the past, and the writings that I see from Juan Conejero say the opposite. And so the technique that I showed you, I didn't invent. It's what I saw Juan do, what I saw Juan write up, and that's how I've always used it. So I understand because I saw the same thing from Adam, and maybe Linda saw Adam's presentation as well, where he produced a local de-ringing support file that just had the largest stars in it. I don't know, probably two different sides of the same coin, but like I said, the technique that I showed you is what I saw Juan do.
Okay, yeah, and I found that I need all this as many stars as I can get in my local de-ringing image, because the smaller ones will ring as well, I've noticed.
Yeah, they'll all ring. So
yeah.
The technique that I showed you, I think comes out with great stars every time. In fact, I've had it come out with great stars every time I've done it. So cool. And the way that I produce the mask is also something that I got from Juan. And I see your comment, Linda. I'll find that right up and try and post it in the comments, but I'll get it to you somehow. Find that write up that Juan did on how to implement this. What was I saying? Oh, the star mask technique that I got from him as well. And I think that produces a really great star mask with linear data. So you don't have to stretch it first and then produce the mask and all that kind of fooling around. Okay.
Cool. Yep, that's all we've got for the moment.
All right, let's dive back in here. So we were talking about local histogram equalization, and this is a function that I think really benefits from a mask. Unlike deconvolution, I think the LHE process can be a little heavy-handed if we don't produce a mask. The unfortunate thing is we don't want to use the image that we have to produce the mask, because then it's going to remain flat. What we want to do is go back to the original HA image that we had and pull back some of the detail that we had there. And if you remember in the beginning of this, I said that I created a starless version of our HA image. This is why. The way that I produced this was I just took the raw HA image that we started with. I took the stream stretch parameters, applied them to a real stretch, dropped it on there, and ran StarNet. I've done nothing else. That's all I did. This is the original HA image with the stars removed. I'm just going to make a copy of that, and we're going to call this LHE mask, so we don't lose track of what the heck we're doing here. And the first thing that I do to produce this mask, or really the only thing that I do to produce this mask, is stretch it. And what we want to do, let me just pull up my stretch here. Let's bring this back to 1. What we want to do is stretch it in such a way, I'm just going to reset this, stretch it in such a way that we harshly clip the blacks and we push up the lights. Okay, so like I said, be harsh on the blacks, drop them down. You can see that I'm ending up with almost no histogram in the output here, because we're going to crush those blacks down and we're going to stretch up the lights. And this is the kind of image that we're going to end up with. So when I apply that stretch, this becomes our mask. I'm going to take this mask and apply it to our image. Move it out of the way here for a moment. You can see here that we are protecting the low signal areas, and we're bringing up the places where we had high signal in the original HA. So now if I bring up local histogram equalization, this is the function that I think, and you know what, I made my screen bigger, and now this sucker is huge. Let me shrink this down a little bit. There we go. Okay. So I think this is a function that you really need to play with to get right, because every image I find is different. I almost never have the same values in this thing, and it's really about appearance more than anything. And so I use the preview window to great extent when I'm messing around with LHE. The kernel radius, you know, you'll typically see that anywhere from about 100, maybe 90, up to around 200 or 300, about 250 or 300. You know, in that range somewhere is where you'll typically find the appearance that you're looking for. I like this one around the 175 mark when I was doing it originally. And if we turn this on or off, if we blink this on or off right now, you can see the contrast that's coming back. But I personally think that's a bit much. And I'm going to turn this down a little bit. We'll take this contrast down to maybe 1.5 and maybe drag the amount down a little bit here. And I'll blink that on and off. And now you can see before and after. We're just bringing back some of that contrast, some of that depth that we had in the original image, maybe just a little bit more there. Yeah, that looks good. So you can see before and after. What we've done there is brought back some of that original contrast, but not to such a degree that we're obfuscating the low signal detail areas that we have in there. So let's go ahead and apply that. And if I zoom in after this is done here, this will only take a second. If I zoom in on this area that I keep calling attention to because there's lots of lines and stuff, you can see how much more detail we're bringing out here now. So if I do sort of a before and after here, before and after, you can see we're really getting some nice detail come up around what my wife refers to as the angry cat in this nebula. You know, you get some real pretty detail coming up here. If we kind of go over to some of these areas here like this, you can see that we're really starting to pull up some nice looking stuff. Let's go over here maybe to this area, and you can see this little you know, this little wall before and after. We're really starting to get some nice detail now. Okay, so that's local histogram equalization. The last thing that we're going to do is sharpen this up a little bit. And so I'm going to use multi-scale linear transform to do my sharpening. Notice that I'm leaving my mask applied that I created during the LHE step. I use the same mask when I sharpen. We want to sharpen the high signal areas, leave the low signal stuff alone, in my opinion. And so sharpening is something that is easily overdone, in my opinion. And this is where we really want to kind of take our time and be careful about how we are applying this. And so let's pull up a preview here, and I'm just going to zoom in on an area like this and see what the effects of sharpening are. Now you notice that I'm also applying some de-ringing here to keep our stars from bouncing around. We'll get the same kind of ringing artifacts that we saw in deconvolution if we're not careful here when we sharpen. But if I turn this sharpening on and off, if we blink it, you can see the before and after. There's before and there's after. We're really starting to sharpen up these details. And I don't know how well this is coming through in the YouTube presentation. I hope you can see that. But we've gone from, in the beginning, what was, I think, a pretty soft and muddy image to something that now has a few razor blade edges on there that I think look pretty good. Now, again, we don't want to overdo it. And typically what I do is I only sharpen in 2 and 3, or sometimes 2, 3, and 4, depending on the image. And I have a bigger number in layer 2 than I have in layer 3. Don't sharpen in layer 1 or you're just going to increase noise. And so this is kind of the method that I use. And I just sort of tune these numbers until I get into a place where I like it. And I usually start too high. So if I just put this, let me just show you, if I put this at 0.5 and 0.1, and you can see what a mess we can make of the image if we apply too much sharpening. To me, that's too crispy, too crunchy. We don't want it to be that harsh. We just want to bring out the detail. And now I can't remember what numbers that I had in here were. Let me just open it back up again rather than guess. There we go. Okay, so I'm going to go ahead and apply this sharpening to our image. And that is it. We should have now our nice sharp HA layer. Now there's one thing that we don't have though. If we look at the original tone map, you see a whole lot of pretty colors and pretty stuff over here on this side of the image, right? And if we look at our HA layer, there's nothing there. Well, these pretty colors that we have are not coming from HA. And if I were to apply this luminance, in effect, to this tone map, all of this stuff would disappear. And I don't want it to disappear because I think it's pretty and I like it. So, but we want to make sure that we keep all of this detail that we just created in the center here. And the way that I do that is, let's start off by creating a mask, and I'm going to use the game script. If you guys don't know or use the game script, go look at it. It's really cool. I'm going to add an ellipse, and we're going to move this ellipse right here, and I'm going to make it a nice big circle like that. And we're going to use this to protect this area of detail that I have. And what we're going to produce is a gradient mask. You see over here where it says the mask that I want to produce is a gradient mask. And I'm going to go ahead and create that. And that looks like this. And if I apply this mask to our image and show it, we can see we're actually doing the opposite of what we wanted, and we'll just invert it. But you can see that the gradient that we produced in the center here is going to be right over top of all the pretty detail that we want to protect. So I am going to invert that mask and hide it again, and can move him out of the way. And now let's yank the luminance out of our tone map. That's a pretty simple operation, one click. And here's all that stuff that we want to add in here. How do we do that? Well, the easiest way, in my opinion, is to use pixel math. And it's a pretty simple expression. If you're familiar with lighten in Photoshop, this is the same as a lighten operation. We're just taking the maximum value of either our original image or tone map. That's going to be applied everywhere except where we have it masked off. Except where we have it masked off. So when we apply this to our image, we see all of this come up all nice and pretty, but we didn't change that. And so if I do a before and after here, before and after, we can see all of that stuff on the left side is coming up nicely, and all the stuff in the center is pretty much staying the way that it was with the detail that we've already brought up. So now we are ready to apply this to our tone map. The way that I do that is with the channel combination tool in CIE lab mode. You can also use the LRGB tool, and frankly, I don't know what the difference is. This is just how I learned to do it, and I'm a creature of habit sometimes. So I don't know that there's any difference in using the LRGB combination tool or using channel combination in CIE lab mode. Maybe one of you guys know what the difference is, but this is, like I said, the way that I've always done it. So we just put our L image in here, and I'm going to apply that to our tone map. And boom, there we go. We get our stars back, all nice and pretty. We get our detail. If I zoom this up and do a before and after here, you're going to see a dramatic change. So if we look at the original tone map, it looked like this, and you can see that it's pretty soft, right? The colors are all there, all of the areas are there, but it's pretty soft. And as soon as we apply that, in effect, luminance layer, and ignoring the stars for a moment and looking at the nebula, you can see that we've got some really nice, sharp, crisp lines. We have lots of detail coming through in here. If we move up into one of these other areas, here we go. We can see some nice, pretty detail coming in here, along this ridge as well. Where's my zoom tool here? Along this area as well. Really great detail coming out of the image now. And we're almost done. I might, maybe I'll bring up a curves. Whoops, yeah, that's what I wanted. I'll bring up my curves tool, and maybe we'll apply a little bit of saturation to just kind of bring the colors up a little bit. I don't want to go too much, something like that. And maybe just a little bit of brightness. Let me reset this limit, maybe just a little bit of brightness here. Something like that. And boom, we're done. That's our finished image.